our last seminar in series 4 of EDT.Community. We have just a couple of intro slides here before handing over to Nelly. One of the things that we're trying to highlight at the moment are the kind of publication deadlines related to digital twins. Hopefully this is of interest to everyone here. So for example, we have a workshop deadline coming up for the FMDT workshop in 2023 in Germany. Submission deadline on the 13th of January next year, so coming quickly. Another one, a conference for ANNSIM in Canada, again, early January deadline for that. And also a special issue in engineering dependable digital twins with a submission deadline of February 15th. So yeah, please make a note of those if they're of interest to you. So in terms of schedule, like I said, this is the last actual seminar in this series of talks. But in 2 weeks' time, we will be having a discussion, a panel discussion, so where we have a few panelists from kind of previous talks. And that should be really interesting. We always get some good discussions out of that. So yeah, definitely recommend keeping that in the calendar. But today we're excited to have Nelly. Nelly is an associate professor in computer science at Durham University since September last year, and has been granted the, I'm going to butcher this name, Leverhulme Fellowship in quantification of uncertainty using Bayesian surprises in 2019. And she's also the principal investigator of the research project 2020 Insights. So Nelly, I'll hand over to you.
Thank you. So, okay, it's already shared there. So thank you very much for the invitation to this seminar. I can see some people there that I know, so hello to those.
Sorry, Nelly, are you sharing your screen?
I am showing here, I think. Let me see. I have to do something else. I think you bounced me back.
Oh,
when should I? Yeah. I have to share again. Sorry. Is that okay?
That's better. Yeah.
Excellent. Yeah. So let's go to start. We are always taking more time than needed. So when I was invited to do this talk, I thought, okay, what is it that I can say that is relevant for the community, a community in engineering digital twins? And then I thought that I'm going to share with you at the end of the presentation some ideas that I have been working on with my PhD student, Huma Samin, who is now a quasi-doctor because she already passed her viva, subject to very small corrections. So, but the point is that those ideas sit on in 10 years of work. So I am obliged to do a bit of a introduction of those ideas that we have been developing for almost a decade now to be able to discuss a bit of what are the consequences or effects on my work now in terms of digital twins. So I have been working for perhaps 6 years now in the idea of developing a Bayesian theory of surprise to quantify degrees of uncertainties. And this is the basic ideas that I am going to talk about today. Let's see, okay. So where I am at the moment, I have been moving quite a lot in the last decade. Lancaster, then Paris, then Birmingham, and now I am here in the north of England, very close to Scotland, where I love mountains. And this is my new home now. I have to admit that I didn't do this kind of graphs there. PowerPoint is playing with me here. Well, these are pictures of my new university and my new city. It's a beautiful city. Please, if one of you would like to come and visit me for a research visit or just being a tourist here, just contact me and we can arrange something. This is a cathedral that is like the queen of the city. Perhaps some of you know that the office of Professor McGonagall is here in this church. You can see all the time, always kids and adults dress up as Harry Potter. So who is in all this presentation and what I am going to talk about? We are researchers on self-adaptive systems and autonomous systems. I am always working on what is decision-making under uncertainty for those to develop those systems, but I always make it clear that I like to develop software and I always try to develop better that software. So my background is a software engineering background, and I have been always applying mathematics concepts, distributed concepts from the point of view of a software engineering person. So I am always asking myself, how can I construct this software architecture in a better way? To do that, I'm always trying to raise the levels of abstraction, because the higher the levels of abstraction, the better you can do in terms of software architectures. Digital twins is not anything else but software architecture concepts. I develop techniques for decision-making under uncertainty. For me, humans are always in the loop. To be able to raise these levels of abstraction, for years now, I have been supporting the idea of runtime models as the runtime abstractions, and it wouldn't be a surprise there when I feel like those architectural models that work at runtime. For me, the idea of digital twins and runtime models are ideas that are very close, and this is something that I am going to talk more about at the end of the presentation. To give a bit of a context, at the moment I am leading an EPSRC project. I'm the leader of the project, and we have 5 work packages there. At the front level, we have work package 1 and 2. And the idea here is that the problem domain of this project is that we support the fact that we need to understand what are the effects, what are the risks, and also opportunities of using machine learning. Machine learning can come up with bunny rabbits that can jump in from spaces where we don't expect them. They can bring up with them surprises. There can be nasty surprises, but they can be also good surprises. And the idea here is that in work package 1 and 2, we are developing techniques to study the horizon of those possibilities in terms of risk and also opportunities. At the back end, work package 4 and 5, we develop machine learning techniques, and we deal with data uncertainty in order to keep, as we lead in work package 3, the system inside of an envelope of good behavior. So that is the story that we have there. We work with people from Warwick University who are now in KCL at the moment. My leader there is now working in KCL, and we work together on developing these ideas for them. And these are some of the publications we have so far. So uncertainty, when we use machine learning techniques or any AI technique or optimization techniques, uncertainty is a big challenge. So we don't know in advance what really is going to happen, but we cannot just hope for the best. Some people tend to avoid it. Some tend to avoid it, but some others say that we need to embrace uncertainty. And I am one of them. This one is me and other people who are engineers, who are developers, who are designers, who are researchers, that we say, I have no idea what is going to happen, but I love it. I love it as a research topic. It's not that this is the system. What we are trying to have is the opposite, is a system that is able to deal with uncertainty. And I clarify that because in one presentation, somebody thought that I was here talking about the system, but it's not, it's us. Developers, researchers, we need to acknowledge the fact that we need to deal with uncertainty in advance in such a way that the system can do better when surprises happen at runtime. So in this talk, I'm going to talk about partially observable Markov decision processes, POMDPs as short, as techniques for quantification of uncertainty, and specifically Bayesian surprises. POMDPs offer me a support reference for architecture for digital twins. And this is a research question for me at the moment. Yeah? And I'm convinced that they are a good example of a reference architecture. I'm going to talk a bit about very early ideas in what is the fidelity of digital twins in this context. And see how we link those ideas or with the concept of digital shadow. So the case study that I usually present is the remote data mirroring, but you could think of this as an architecture of microservices, IoT, or any networking system. The idea here is that there is a functional goal, the RDM, has as a goal to protect data against loss and unavailability. To do that, it has two topologies, the minimum spanning tree one and redundant topology. So redundant topology is when you have a redundant architecture. Yeah, it's a very expensive one, but offers quite a maximized reliability. Minimum spanning tree is, it refers to a network protocol where the idea is that you are going to connect a minimum set of nodes in order to keep the remote data mirroring working. So the system should decide, depending on what is happening in the environment, the system, the RDM in this case, is going to decide if it is going to keep itself using the MST topology or is going to go to redundant topology. And the idea always is that those decisions are going to be made based on the trade-offs between the optimization of different quality protocols. So minimization of costs, maximization of performance, and maximization of reliability. For example, one of the trade-offs here is that if you use MST, it is quite good for minimization of costs, but its behavior is poorly in terms of maximization of performance and reliability. However, if the requirement says that it doesn't matter minimization of costs, the system might then decide to go for RT. What is the sources of uncertainty there? The failures of links, varying ranges of bandwidth consumption, yeah? or even prices in the levels of energy consumption could be different sources of uncertainty that the system can take into account in order to reconfigure itself from one topology to another. The same kind of characteristics can be pretty much generalized into an IoT networking system or balancing of a load in cloud computing, to say something. One of the things, the concept that I also support is the requirements awareness. The systems, I depart from the fact that the system should be aware of how the requirements are going to be met, how well they have been met at some point. And one of the things that we inherit from it is that if we are talking about explanation, the system can explain its behavior in a language that is closer to a stakeholder. So that's the reason why I support the idea of reward-aware systems. So the idea here is that, and it's something based in this very recent work with Humasamin from this year in SOSIM, is that we depart from the fact that a specification model S of the decision making include the trade-off and the alternative adaptations, topologies, and priorities of the qualities. Priorities is something very important because this is what is going to be taken into account by the system when decided which one is the choices that it is going to be made. As the specification of those models is always going to be derived by analysts from the requirements and the knowledge domain X of the system we are developing. S will remain a valid implementation of R if and only if does not change from the moment that S was built until the moment requirements compliance is assessed. And if we are assessing the requirements at all time, it might be the case that knowledge will change, and then it means that this property here will be broken. Okay? So what we have to do here is that there is we need to monitor these requirements compliance according to the knowledge that might be changing, and then the specification model of that decision making might need to be updated accordingly. That is the idea here. In terms of the techniques that I use to monitor that system, because that is the idea here, that we are monitoring the requirements compliance during runtime. So we rely on different techniques. One of them that has been for me quite productive is a technique of reinforcement learning. So before coming up to talk about what is that technique, I just want to come up with the minimum agreement that we need to know about reinforcement learning. So in RL, an agent observes a state of the environment. This agent is always observing this environment, applies an action depending on the state that it has observed. A decision process is runs, and an action is going to be applied on the environment, and a reward is going to come up due to that. Yeah. And then another state, the environment may will have a transition from one state to the next state. That is the idea of reinforcement learning. I use Bayesian learning in order to as the base technique for this, and this is the one I want to talk about now. Before going to POMDP is a kind of a variation of MNDP. So what is a Markov decision process? It's a tuple of 1, 2, 3, 5 elements. Yeah. S, that is a finite set of states. A is a finite set of actions. P is the probability transition matrix, transition probability matrix, which contains all the possible transitions that say that given a state S in T and an action A, it is going to describe which one is the probability that the system goes to a state ST1 that is equal to S prime. For each possible transition, there is going to be a reward function that is going to be positive or negative. So in the end, the average of those rewards is going to be processed somehow. I will explain later. And then the MDP is going to choose the action that is going to maximize the reward. Yeah. We always are going to have this element here that is the discount factor that is going to be a number between 0 and 1. And what it does is that it is going to, in the projection, it is going to somehow describe how far into the future you are going to go in order to support the decision making. In the case of partially observable Markov decision processes, the argument that I make there is that if we are talking about autonomous self-adaptive systems, we don't see, we can just partially observe the system. We cannot exactly say how reliable is a system at one point. We can just infer how reliable it is based on monitorable variables. That is the observations here. So in one of the papers of Sasso 2018 and Siemens 2019, with Luis Paucar Garcia, a previous PhD student, we came up with the mapping of how we could cast, or how we cast, the decision-making of self-active autonomous system, how we can cast it as a POMDP decision process. So here the idea is that we have observations over the states of the system. Those observations are going to be monitored by the agent. The agent will, depending on some rewards, will make a projection into the future and will come up with the action that is the one that is going to maximize the set of rewards in the future. Yeah. So in order to do that, a POMDP is a tuple in this case with not 5 elements, but 1, 2, 3, 4, 5, 6, 7 elements in the tuple. As previously, it is going to have a set of actions, transition functions, but it will have now the observations. It will have the observations, the rewards again, and the transition probabilities, yes, and the discount factor as well. So what is important here is that we have included these observations that is not anything else but the monitorables over a system, an autonomous self-adaptive system in this case. So in the case of the POMDP, what we have then is a system in time 0. An action is going to be established. A reward is going to come up, yeah? And then it means that a new state is going to come up. The system is going to transit from one state to the other, and it means that the observations are going to change. Obviously, if you come up from, for example, a system that is using MSD, and the system is transferred into the next state that says that the system is using redundant topology, then the observations will change. The observations, for sure, they should correspond now to a system that is more reliable, but also less cost effective. Yeah. And like this, the system is going to come up, and new observations will show up, and the system will, the managing system will keep monitoring the managed systems. Several rewards will come up, and then perhaps the manager system, that is the decision maker, will decide that the system might have to transit to another state just because for the requirements to be met, that new action is the one that should be applied, that reconfiguration action. And this is going to be to the end of the system, yeah? So different, so see here that I see the system, but in fact, in the case of the POMDP, what I don't see the system as such. What I have is a system that is partially observable. So what I have are beliefs over that system. So the system, the decision maker believes that the system is 85% satisfying reliability, yeah? And believe perhaps that the system is 78% satisfying the minimization of costs. And based on those beliefs, the recuperation actions are going to take place. So that's something very important between the difference between this slide, that is the one that thinks that you see all the properties of the system, that the system is fully observable. No, in a POMDP, what you have is beliefs over that system. What you have is like partial pictures of the system given by monitorables and that are going to use to infer beliefs over the system. Obviously, those beliefs in terms of when you use POMDPs, they are translated into what is the levels of satisfaction or belief over the level of satisfaction or probabilities. Okay. So, and this is, yeah, this is the same what I have been telling you about, but in a graphical way, yeah. So the RDM is the environment that the POMDP, the agent is monitoring all the time, yeah. So the agent is the decision maker, or what is called in terms of in the research community is the manager system. And the RDM is the system that is managed, the managed system. This managed system has a state, but there is a barrier here. There is a barrier. The agent here, what sees are observations. It doesn't see the complete state of the system. Given a reward, having come up with an action, there are a set of rewards that, in fact, in the case of Humasamin, she doesn't use one scalar reward. She uses a vector of rewards. So she's able to reason not just about one reward that is going to be maximized, but she talks about, or she reasons, she's able to reason about different rewards that are associated to different goals that are going to be optimized. Like, for example, in energy consumption, reliability, costs. What does the POMDP uses for this? What it uses is the famous Bellman's optimality equation. And here is the discount factor. The discount factor, what it does is it kind of limits the path into the future. How far away into the future the POMDP is going to go in order to come up and say, this is the action that is going to maximize these rewards. Yeah. So this is as well in terms of for people who don't like to use machine learning as such, this is an optimization problem. Yeah. It's 10 years ago, we wouldn't be talking about machine learning. It's an optimization problem that we use here. Okay, so if we see it as an architecture, this is the way how a person, a person that works in optimization or reinforcement learning, they see the problem. But if we see it as an architecture, as a software architecture, this is what we have. We have the managed system that is the RDM, or any other system that I have. Another problem that I have solved, for example, is an IoT networking system. So the managed system has effectors where the actions are going to to be applied, and that has proofs that are the monitorables or the observations. Yeah? The managing system, that is the decision maker, is going to monitor, is going to analyze, is going to plan ahead. This is the Boltzmann equation here, and according to the rewards that are going to be maximized by a given action, that action is selected and is going to be applied onto the RDM. Yeah. Hopefully, so then this is where the knowledge can change. And we know that the knowledge has changed because we have monitors here. And it means that the system need the knowledge change. It means that the decision-making model use needs to be updated. And that is the reason why the POMDP is going to be able to foresee again or forecast what is the action that is going to maximize the requirements at the moment with what I have at the moment. Yeah, and this is the loop that the system will continue there for a long time while the system is running. If you want to know more about it, these are two key publications that we have there. So before coming to what is the surprises itself, you could see here that what I am doing here is that I have the system here, I have the POMDP. This is for me the runtime model here. The POMDP is for me one of the many runtime models that system can have attached. And for me, this is the basics of the digital twin. Yeah, this is the basics of the digital twin. That is the digital twin associated to the decision making. Yeah, and that's pathological regression. I'm going to talk about it later. So during that decision making, we always need to quantify the uncertainty, to quantify, for example, the risks. How risky is this? Humans, we think like that. How risky is this bet that I am going to make? How risky it is? You quantify that risk, you quantify the uncertainty that you have over that risk, and then you decide if you are going to make an investment or not. Yeah, that's that, and that is the way how I think and I get inspired in order to model the decision making of the systems I work with. And this is a paper that I got that explain a bit the concepts of this. So usually what happens here is that we always target the success, yeah, but it's not always we are going to have. Sometimes we are going to fail, but sometimes we might not be in the target. But it doesn't mean that the system is dead. It means that the system is meeting the goal, but perhaps with a low level of confidence, but it's still meeting it, and perhaps can recover itself to come back here to target. So these distances here is what we want to foresee in advance somehow. So to do that, in order to measure those dimensions of uncertainty, and working with what is the concept of surprise. So surprise is a brief emotional state experience as the result of an unexpected event. Yeah. So as in with humans, what I foresee is a system like us. If I get surprised with something, then I might decide to avoid a choice, or it might say no. That's another choice that I will choose. Yeah. So there are big surprises. There are even bigger surprises. But we have as well as small surprises, yes? We have even, emotions that they are not even a surprise. They you know, somebody's telling me, oh, you lost your mobile, and I would say, oh, are you kidding? Really? I have not lost my mobile. So it means that I am not going to take any action about it. But in big surprises, I might go quickly and perhaps cancel the credit cards that I have engraved in my mobile. So this is the kind of behavior that I foresee in the system, and in spite of how humans we behave, I would like the system to behave in similar ways. How do I do that? So I measure surprises. The idea is that we can measure our own surprises. How do I measure surprises in a system? One of the aspects of surprises is the uncertainty and subjectivity. So what is a surprise for me might not be a surprise for another person. Also, two events, the same event shouldn't be surprising twice, or at least 3 times. So when an event happens once and then again, the effect of surprise might come down. So I have to take into account how to model that in a mathematical way. So, but first thing, how do I measure a surprise? So the key idea here is that a surprising event can be defined as one that causes a large divergence between the beliefs prior and posterior to an event. The nice thing with the POMDP is that I have beliefs before and prior to an observation. Yeah? So the POMDPs or any other technique that allows me to have probabilities before and after the event in a decision-making process, they are giving me a very nice trace in order to measure surprises. So what is the idea here? That if a surprise is huge, then somehow the system should react immediately accordingly. But if a surprise is small, perhaps we can use languages like relaxed language or an implementation of a similar technique where we can just, you know, require from the system, stay quiet, there is no need to be in a rush, let's go to observe what is this situation that is coming up. So that is the idea of the surprises. I'm working with the problems that I have with surprises, how I keep the novelty of a surprise, because the point is that if an action is already surprising me, it is not going to surprise me again. So mathematically, we are using different corrections where I hope that it's going to keep my Bayesian surprise theory even stronger now. There are keep tuned with this because we have a very good publication so far that might be a publication next year. So I want to start closing the presentation, just coming up with this graph again. So one of the ideas that I want to say here is that this is for me an architecture. This is the POMDP here. The POMDP corresponds with the decision maker of a given system. Yeah. So I have beliefs. So I have observations, and from those observations, I have beliefs about how the system is meeting the requirements. So one of the ideas that we are doing now is that if I declare that this is my digital twin associated with the decision maker, we are applying logistic regression to see how well our beliefs are, how well they are articulated with those values or observations over the system. So there we have as well very positive results, because so far I am able to characterize how well the decision making is working. So in the end, what we used was logistic regression in order to evaluate our decision maker. But then we realized that if we see this as a digital twin, this plus the simulation system or the simulations, what we have is somehow we have defined a measure of how is the fidelity of this digital twin against the managed system. So far what we have is that for us, digital twins are the models at runtime plus the simulations. We have way how to use using logistic regression. We can define the fidelity of this digital twin. And the other thing as well that was something that came up in a DAX-Tool seminar associated to this community as well is that surprise, surprise, it is not twin, you got triplets. Meaning that sometimes this digital twin might not be causally connected, attached to the system. And in that case, what I have is a digital shadow. But as soon as this is causally connected to the system, meaning that if the digital twin changes, then the system is going to change. And if the system changes, and then the digital twin changes, it means that this is a digital twin. But if we don't have this element here, and we are using the POMDP, for example, just to study, but not to enact an action, this is for me a digital shadow. Yeah. So, and this is what I have talked about, uncertainty, using logistic regression and Bayesian surprises in order or Bayesian surprise and logistic regression in order to support the concepts of digital twins based on models at runtime. I'm working on the idea of fidelity of my concept of digital twins. And one of the ideas is that these can be used in any optimization or machine learning techniques where you can attach levels of confidence. Other things that I have not talked about is that how I use, I'm very, very proud of this work with Antonio Garcia Dominguez, who is now in York University, about temporal models for history-aware explainability. And I could see, for example, that these are another aspect, another digital twin of the system as such. So thanks for listening. And if you have any question, please let me know. Thank you very much.
Great, thank you, Nelly. That's a really good talk. I don't know if we can get some virtual or real